Okay, in this video, I thought we'd take a look at the transformations of tangent and cotangent using Desmos. It makes a nicer graph, and it's really a lot easier to uh, show you what the different transformations do rather than doing it by hand. So let me start by, I've graphed y equals the tangent of x here, f of x equals the tangent of x. And you can see that it goes from 0, 0, and I believe if I click somewhere else on the graph, I could get other values of x comma y. Let's see what happens at about pi over 4. Now, there's 0, there's pi over 2, so pi over 4 is going to be halfway in between. So if I click and go to about there, you can see that at pi over 4, tangent is 1. And that's what we expect. That's what we learned when we learned how to graph a tangent. So now the question is, what do transformations of tangent look like? Well, I'm going to start by graphing g of x equals the tangent of x. And you can see I'll put the graph in a different color. And then I'm going to add a letter A in front of tangent x. And you can see it says add slider, and it gives me the A that I typed in here. If I do that, then it gives me this slider tool that I can move around to see what changing the coefficient of tangent, the number in front of tangent, does to the graph. And you can do this manually. You can see what happens when you get to a negative value. It flips the graph, it flips the tangent graph over. In fact, when a is negative 1, let me see if I can get there, it looks exactly like the positive 1 tangent x. Positive 1 times the tangent of x is like the negative 1 times the tangent of x, except that it's been flipped over the x-axis. Right? This graph here, flipped over the x-axis, produces the yellow graph. So you can play around with that slider and see what it does. It's pretty cool, I think. Now it looks like a straight line out here, but what's happening is that this curvy, slopey bit that eventually turns into an asymptotic, it's still curved here, but it looks like a straight line. That's happening much faster here. So it's not really a straight line, it just looks like one. You can also animate the slider that you've put in place by just clicking on the play button. You can stop it by pressing pause. I'm going to set it back to about 1. You can also change how far you want it to go. Right now it's going from negative 10 to positive 10, but let's say you want it to go from negative 5 to, let's see, negative 5 to 7. There we go. And that's what will happen now, is it will only go down to negative 5. So we won't quite get that complete straight line look, although we still almost do. And change it to like negative 2 to 3 or something. What happens then when you animate it? You can see that it only goes to that point. It doesn't quite get all stretched out the way it did when we had it going all the way to 10. Another thing you can do is change the step. Right now there's no step in there, but let's say you wanted it to jump from x equals negative 2 all the way through x equals 3. But instead of going kind of continuously like it's doing, say you only wanted to look at every pi over 3. Now when you press the play button, it jumps in increments of pi over 3 instead. So there's kind of a lot of cool stuff you can do. The point I wanted to make with this, though, really is that I think I'm just going to go from negative 2 to 2 for now, is that this value of a, whatever's in front of tangent here, has the effect of causing the graph to change, kind of morph. But when you look at in what way it's doing that, it's actually stretching it. So let me get it to something bigger than 1. And you can see that the graph is stretched. Now, if this had been a quadratic instead, that might make sense to you, right? Let's go all the way to 2. If this were a quadratic, then 2 times that quadratic, the graph would be stretched, right? All of my y values, every x value, let's go over to a positive x, every x value has an associated y value. Well, with the 2 times the tangent, that same x value is going to have a y value that's twice as much, okay? So that's what's happening with a. Now, I can also add a number in front of the x, in front of the argument. And it asks me, do I want to add a slider for that one? And I say, sure. I'm going to set A back to 1. Come on. There it is. And then I'll animate B. Now B is going from negative 10 to 10 at the moment, but let's just see what happens. I'll slide it manually first. And it looks like we're getting more copies of tangent the bigger B is. What happens if it's between 0 and 1? Well, we get fewer copies. And let's go ahead and animate it. And if it's negative, let's see what happens when it's negative. Well, it flips the graph over again. So once again, I'm going to restrict this from, well, let's say, I guess I can say negative 2 to 3 again. And I'll leave my step continuous. Maybe I'll change it to 1 just for the moment so you can see what happens. It'll jump from where B equals 1 to B equals 2 to B equals 3, and then back to 2, 1. When B equals 0, we get nothing. And negative 1, negative 2. It jumps around instead of being smooth. And you can click on B and just remove that if you want it to be continuous again. You can also speed these up and slow them down. If you click on this guy right here, this arrow, you can make it graph much more slowly, make it animate much more slowly. I find that quite helpful because then you can really study what's happening. Or you can speed it up, or you can ask it to loop in different ways. Okay, now I'd like you to recall that I made A 1 again. So right now this is graphing 1 times the tangent of bx. It's like graphing the tangent with a b or some number in front of the x, but there's nothing in front of the tangent itself, right? Remember that with sine and cosine, we called this number the amplitude, and we do that with tangent as well. It's still called the amplitude, although the graph kind of goes on forever. It has the same effect of stretching the graph as it did with sine and cosine. B, though, is, I'm not sure what to call B, but it's the number that tells us about the period. It is not the period itself. Remember that the normal period of tangent, let's make B 1. Normally the period of tangent is pi. It goes from negative pi over 2 to positive pi over 2 without a break. I'll graph the lines x equals negative pi over 2 and x equals pi over 2, and you'll see what I mean. Okay, see these vertical lines here, x equals negative pi over 2 and x equals pi over 2? Those are asymptotes. And I have one continuous infinite cycle of tangent that goes between these two. So the period of tangent is pi. That's how long it takes to complete one cycle. This number here, the number b, tells us how many cycles of tangent we're going to get between negative pi over 2 and pi over 2. Right now we have 1 because b is equal to 1. We have one cycle in that range. If I change b to 2, I think I can just do it by typing it in there too. B equals 2. Now you can see that between negative pi over 2 and pi over 2, I have, starting here, I have a positive half of a cycle, a full cycle. I'm looking at the yellow graph, and then a negative half of a cycle. Here, let me turn the blue graph off. I have a positive half of a cycle, a full cycle, and then a negative half of a cycle. And that's a total of 2 cycles. So this number here is how many cycles I get. So that number is not the period, it's how many times you get a tangent graph in the normal period. If you want to figure out what the period is, you take tangent's normal period, which is pi, and divide it up into that many subsections, if you will. So pi over 2, pi divided by b, pi divided by 2, is the period of a tangent of bx, where a is 1, so tangent of 2x. Tangent of 2x has a period of pi over 2. Well, sure enough, the period, there's a positive half of a period there, and a negative half of it, positive half of a cycle, negative half of a cycle. Together they make one cycle between 0 and pi over 2. So I have a period of pi over 2. And I got that by taking the normal period for tangent, which is pi, and dividing it by b, this number right here. Okay, now I can also add something to the argument. But again, it's going to ask me if I want the slider, so I'm going to say yes. There's my C slider. And C can go from negative 10 to 10. I'm actually going to change that because I can tell by what it's doing here. and it makes sense to me because if it's inside parentheses, it's going to move it to the left if c is negative, and to the left if c is positive, to the right if it's negative. The bigger c gets, the farther to the left it moves. The smaller c gets, the farther to the right it moves. When c is 0, I'm not adding anything. I'm not shifting horizontally at all, so I'm back to normal. So because I'm shifting to the left and to the right, let's change my left and right bounds here from negative pi to pi. And that just means that I'm only going to be able to shift it so far. This point right here will only be able to shift to negative pi and to positive pi. Also, though, I'm going to have it jump by pi over 12. So that when I animate this now, you can see it sort of jumps from one iteration to the next. I slowed it down a little too much there. Okay. So now I have, I'll stop it, negative pi. I have moved pi units to the right. So the point that used to be right here is right here. Okay, so we've looked at what happens when we put a number in front of tangent, in front of x, and what happens when we add to the argument. There's one more thing we can do to transform a function, and that is we can add a vertical shift. We can add anything we want to, where is d equals 0? It's right there. So that's my tangent function. Let's put c back to 0, b back to 1. So right now what you see in orange here is 1, that's my a, 1 times the tangent of 1x plus 0 plus 0, which is just the tangent of x. In fact, if I turn this one back on, you'll be able to see that's the same graph, right? That's just my tangent of x. Let's go ahead and leave that turned on. What happens if I change d now should be that the graph moves up and down. Up for positive and down for negative d. And move it up, you'll see that it's the same shape of graph. It kind of doesn't look like it, does it? But it's really just moved it up to here. So in short, we can do the same things for tangent as we did for sine, cosine. We can do the same things for tangent as we did for sine and cosine. And as we'll see in a minute, we can do the same things for cotangent as well. As it turns out, we'll be able to do the same things for secant and cosecant. So I'm going to stop this video here because I'm running out of time in this limited edition of Desmos, and I'll pick up where I left off in the next video.